Okay, now we go on to calculate the energy relations in a wave. Again, amplitude A, angular frequency omega, mass density mu, and we're going to invoke a tension F, so that the difference between what we just did and now is we can actually calculate the speed of the wave that we're going to need. So that we do the same thing, small increment delta x, mass is mu delta x. It undergoes simple harmonic motion, angular frequency, omega, and amplitude A. Didn't mention that, didn't write that in. The contribution to the total energy in the wave then from this increment is the same expression we got before, 1/2 the mass times the maximum velocity squared, being the maximum kinetic energy, but that's the total energy at any time. That's the sum of the potential plus the kinetic. That's the total energy we have to have in the wave, the total energy we have to provide the wave in order to get this mass increment into simple harmonic motion. Okay? Now, if we want the energy per unit length, well, this is the energy in length delta x. We divide that by delta x to get this, so that delta x just goes away, and here's our energy per unit length. Now, if we know the energy per unit length, how do we figure out how much energy we've got to supply per unit of time? Okay? You might want to stop and think about that. Just try to get your head around that particular question. But it comes out that, well, you would multiply this energy per unit length by the length of wave that you have to create per unit of time. And the length per unit of time is just the speed of propagation. The wave develops at a rate equal to the speed of propagation. So that's the length you get per unit of time, the additional length to which you have to provide this energy per unit of time. So we multiply that out. Now, the wave speed, of course, is the square root of f over mu. So we just write this expression like so, replacing c with square root of f over mu, and then we do a simplification. Square root of mu in the denominator, mu in the numerator gives us a square root of mu in the numerator. And this is the expression I believe your book gets for the power in a wave. Now your book goes about it in a slightly different way. So let's preview that, and then we'll do a quick supplementary video to flesh this out a little bit. The power exerted by a force F moving at velocity on a mass moving with velocity v is just F dot v. Okay, and that's basically something you should know from first semester. We'll discuss it a little bit when we expand this, but that's it. Now, F dot v, F is a vector, and it's a vector in the direction of the string at whatever point you're looking. The increment that we looked at before was kind of at an angle like this. Okay, now these angles are assumed to be very small, so that you think of the force being at the in the direction of the increment, the velocity being the perpendicular velocity of that mass increment. The increment itself is moving in this direction. The force is in the direction of the wave. So that dot product is going to be the product of what? Well, first of all, the velocity is just the partial derivative of y with respect to t, where y is your wave function. And the force is going to be F times the sine of whatever the angle is between the direction of the wave and the direction of the string at that point, and the direction of the equilibrium position, the direction of the axis. And it's going to turn out that that's just F times the partial y with respect to x. Partial y with respect to x is basically the tangent of this angle, which is equal to the sine of the angle for small angles. So that what we have here is like f times the sine of theta. We multiply that by this. So the partial of y with respect to x, as we've seen from the wave function, is just the wave number k multiplied by the sine of kx minus omega t, let's say. And the partial y with respect to t is omega times a, omega times the omega a times the sine of the kx minus omega t. And from all that we get an a squared times the sine squared of the kx minus omega t, k being the wave number, which is the speed of sound, or the speed of the wave times the angular frequency, and the average value of the sine function being 1/2. This ends up being equal to this. Now, showing algebraically that this is going to be equal to this is easy, but understanding where these partial derivatives come from, we're going to supplement that in a minute.